Good morning, everyone. Welcome to today's hearing. Today we're going to hear evidence from two of the expert witnesses instructed by the inquiry, and we're going to hear it in the form of presentations. Yes, Ms. Grange.
Yes, good morning. Good morning, Mr. Chairman. Good morning, panel members. So this morning, Professor Torero will be giving a presentation based on his report entitled Determining Performance, the Adequacy of the Current Testing Regime. And he's going to be presenting this morning and then answering questions on that report later. And he will be dealing today with the role of the fire safety strategy, in particular in relation to a regulatory system that has functional performance requirements as opposed to prescriptive ones, what performance objectives are relevant and should be considered, how the relevant performance objectives can be understood and quantified scientifically, how the current testing regimes produce data and how that data can or cannot be used to understand the relevant performance objectives, the testing of products and systems to produce data, and who is responsible for fire safety in buildings and the competency they require to perform that appropriately. So those are the topics he will cover.
Thank you.
And this will be an oral presentation. I do need to give a trigger warning. Several of the slides that Professor Torero's presentation, in his presentation, contain images and videos of fires, including fires inside homes and in tall buildings. And there are also images of the interior of Grenfell Tower post-fire. So I give that trigger warning now. And it's important to warn anyone watching who prefer not to view that content. So could we perhaps call Professor Torero now?
Yes, thank you. Good morning, Professor. You're going to affirm, I think, is that right?
Yes.
The words are there on the screen. Would you read them out, please?
Okay. I do solemnly, sincerely, and truly declare and affirm that the evidence I shall give shall be the truth, the whole truth, and nothing but the truth.
Thank you very much, and welcome back to the inquiry.
Thank you.
Okay. Yes,
Yes.
Ms. Grange.
Yes, Professor Torero, thank you very much for attending the inquiry again and assisting us with our investigations. It's very much appreciated. If we can please bring up your report that you're going to speak to today and also next week. It's at JTOR 706.
Before we look at that, Professor, I note you're still standing. You know, of course, you're very welcome to sit down if you would like to. I understand that you might prefer to stand, but if you want to switch between standing and sitting, please feel free to do that as well.
Thank you very much.
As long as there's a chair provided for you.
I'll find one.
Well, I'm sure we can do that, yes.
Yes, so if we could have the report up on the screen. There we have it, Phase 2, Grenfell Tower Inquiry, Adequacy of the Current Testing Regime. And we can see it's dated January the 4th, 2022, and there's a signature. Is that your signature?
Yes, it is.
And if we also look at page 7 of your report, it's entitled Statements, and there are various declarations there. Again, is that your signature at the bottom of the page?
Yes, it is.
Now, have you provided that report in the same way that you would have provided a report to a court?
Yes, I have.
Can you confirm that the facts and matters set out in this report are true to the best of your knowledge and belief?
Yes, they are.
Can you confirm that your report represents your true and complete professional opinion on the matters addressed within it?
Yes, I can confirm.
And today you'll be giving a presentation about that report, and then you'll be asked questions about it next week.
Yes.
So please, would you go ahead and give your presentation?
Thank you very much. Okay, thank you very much. So before I get started, as Ms. Grange said, this is about the report that I wrote, and it focuses on determining performance and the adequacy of the current testing regime. And I would like you to bear with me as I cover some background information that I'm sure you've heard many times already, but I do think it's necessary to set the context for the rest of the report. And I think that it addresses, this background information addresses a number of general issues that pertain to fire safety strategy and the role of a fire safety engineer that I really think is important in trying to understand what expectations we must have in regards to the performance of systems such as the building envelope of Grenfell Tower. So I think the first thing that needs to be addressed it is a contextual issue. So when we're talking about fire safety, the first thing that we really need to recognize is a very multidisciplinary space. You've heard evidence from architects. On Monday, you heard evidence from Mr. Lay, who is an aerospace engineer. You've heard evidence from Dr. Barbara Lane, who is a structural engineer. I myself am a mechanical engineer. And we have all found ways by which we have educated ourselves to try to understand, the different aspects of fire safety engineering. Nevertheless, fire safety does not have a common language. And therefore, there is a number of elements of information that many times are very difficult, to translate. And therefore, when I am describing certain things as a mechanical engineer, an individual with a mechanical engineering background, I need to be extremely explicit in the way in which I present things to make sure that others can understand me appropriately. Now, in a similar way, when we apply fire safety into buildings, we have to recognize that buildings are going to outlive the designers. And we are designing them to stay for a long period of time. And therefore, there has to be a very clear record of those elements that pertain, to the fire safety strategy, so that those elements can be used through the life of the building by the multiple stakeholders. And that's the final point of context, which is the fact that there is multiple stakeholders. And those multiple stakeholders range from the occupants that are not required to have any knowledge on fire safety matters, to the fire brigades who have a certain aspect of knowledge pertaining to their activities, to people that are doing fire risk assessments and so forth. So those multiple stakeholders, again, come from very different backgrounds and therefore require to have a very explicit, representation of the information that is available. And this is why I very strongly believe that documentation is absolutely essential in fire safety, because it is the way by which we not only transfer the information, to the multiple stakeholders for a very long period of time, but also the way in which we establish the language that we're going to be using and everything that that language implies, among people that might have very, very different backgrounds. Mm-hmm. Now, this pertains in a very critical manner to a slightly different aspect, which is many times complicated by regulatory frameworks. When we design a building to be fire safe, one thing that is absolutely clear is that fire is a very complex problem. And in our design methods, there are going to be very significant assumptions. And those assumptions need to be documented because they are not trivial. And not only they're not trivial, but they're not absolute assumptions. I can make a set of assumptions that brings me to an outcome, but I could reach the same outcome with a completely different set of assumptions. Now, when I change the assumptions, one of the things that I actually change, and I would like to emphasize this throughout my presentation, is one of the things that I change are the dependencies. So this is the second level that needs to be understood, because if I make a set of assumptions, I will create dependencies between different components of the fire safety strategy that might be completely different to the dependencies that I create if I made a completely different set of assumptions. So the relationship between assumptions and dependencies is extremely complicated and is one that really needs to be explicitly addressed, particularly because many of those dependencies can lead to conflicts. Sometimes I can introduce certain type of measures that are in conflict with other measures and will only work if, for example, they operate in a sequential way. But the moment the two of them are required to operate simultaneously, then you might introduce a conflict. A perfect example of that will be the use of sprinklers next to a smoke management vent. So the sprinkler performance is determined by the flow of air or the flow of hot smoke that passes the sprinkler. So if I put a massive vent to evacuate the smoke, which is a different measure, then what I will actually result is in a situation where I have created a conflict. Now, if the sprinkler activates before I open the vent and I create that sequence, both the sprinkler and the vent will operate appropriately. So the need to be able to understand the sequence of assumptions leading to dependencies and potentially to conflicts is something that is fundamental and is very specific to each unique fire safety strategy. So without the privilege of having all that information explicitly written, we are creating an enormous potential for confusion at the moment where different stakeholders have to make decisions. So in essence, I wanted to contextualize this by saying that all the things that I'm going to discuss through this presentation, I believe are things that should, in principle, always be documented. And they should always be documented and making sure that at each point we're explicitly clear about our assumptions and the language that we're using. So I excuse myself for using the language that pertains to my own background, and I will try to explain things in as much detail as possible. But please, if at any point you believe that I should stop and explain something on the side, I'll be more than happy, to do that, because I do recognize that I'm explaining things from my own personal background. So I think the first thing that needs to be understood, from the beginning, is that if we are going to design something, we need, to have a target. So we need to be able to understand explicitly what is the objective of our design. And in the case of fire safety, the real question that we need to answer is, what is a fire-safe building? Now, for certain systems, that's a very trivial and simple question to ask. If you're designing a gearbox for a car, you might define that as 1 million cycles in the testing regime. So you define a very clear testing regime, and then you apply 1 million cycles in that, and if the gearbox doesn't fail, then your gearbox is appropriate. So here you have a very clear performance criteria, which is 1 million cycles in this specific testing regime. There are other cases where it's a little bit more complex. So if you're trying to design a seat and a seat belt in a car, then it becomes more complicated, because now you have to cover a wide range of individuals. So, it's not the same thing, to have an impact with a child sitting in the car than having an impact with an adult, sitting in the car. So you're going to start creating in the testing regime the possibility of expanding, your the way in which you conduct the test, so that you could cover the potential range of users that you're going to use in the car. Nevertheless, you are going to quantify the way in which you conduct the test in a manner such that it represents in an appropriate way what you would expect will be for example, a collision in the case of a vehicle. And then you apply performance criteria. So you will probably apply a performance criteria that is in no part of the dummy that is used, for the test, the pressure will exceed a certain threshold. So when you're designing a system and you're testing against the system, you have a very clear and well-articulated quantitative and explicit performance criteria. So when we say, what is a fire-safe building? The first question that we should be asking ourselves is, what is the performance criteria? And this is something that I struggle very much, because obviously when we are trying to define a quantitative and explicit performance criteria, and it pertains the matter of fire safety, we're clearly addressing the fact that we are dealing with people's lives. So being explicit about what is the performance criteria is a very, very difficult task. And people will argue that if I make a very simplistic statement, like nobody should be affected in a negative way by the fire, that becomes an impossible task. Because within the variance of people and the conditions in which people are going to operate and so forth, it is an impossibility to guarantee that everybody will be unharmed by the fire. So instead, we could modulate that and take acceptable criteria that are used generally in regards, to life safety, and say nobody should be harmed or nobody should be negatively affected, when it comes to a fire, to a reasonable probability that could be defined quantitatively as 10 to the minus 6, 10 to the minus 8, 10 to the minus 9. But all these discussions are essentially bringing us to a position in which we do require to make an explicit statement of what is the target performance that we are going to expect, from our building. Now, this is something that it is important for me to state from the beginning, because clearly, as we will see later, this explicit performance requirement is not something that is written within our building regulations. Our building regulations have no explicit performance requirement, which eventually leads people to try to use comparative performance requirements. Not as bad as, better than. And the than, or not as bad as, is something that is mostly associated to guidance or prior examples or other applications. So we're trying to compare what we're doing on a specific design with something that was done before. Now, obviously, if that's what we're going to try to do, if we don't understand explicitly what are the assumptions, the dependencies, and the conflicts associated to those examples that are given in our building regulations as guidance, then we will never be able to extrapolate that into our appropriate design, which is effectively the definition of competency. What we have is a situation by which we are constantly extrapolating because we do not have a definition of safety. What we have is just examples of what works, and we are requiring the professionals to make that extrapolation. And in a space that is truly multidisciplinary, and is a space where language is very much confused, and in a space where this information then needs to be conveyed to a group of stakeholders that range from stakeholders that have no responsibility for knowledge to stakeholders that in theory should have great responsibility for their competency. So in principle, we've created a space in which the responsibility on the competency of those professionals making those extrapolations is very high, because they will define what is a fire-safe building. So having cleared that up, then we can start looking into the process of how we actually establish a fire-safe building. So I'm taking this information from my Phase 1 report, and basically I'm going to walk, through the concept of how we attempt to implement a fire safety strategy that delivers an adequate level of safety for a building of the nature of Grenfell Tower. So if you look at this building, it is a tall building, and it is a residential building, is occupied by people. The people who occupy this building are not deemed to be responsible to have any competency in matters of fire safety, and therefore should be guided through the whole process. There is an expectation that they will be guided through the process to a point where they are actually safe. Okay? So how do we achieve this? So basically, if we have a fire, the first thing that we try to do is make sure that we have alerted people. That is our notification, and that is the level of knowledge that we have imparted on the occupants, that they should recognize an alarm. So that alarm is generally delivered by a detector, and there's a technology for the smoke detector or the temperature detector that will deliver the alarm in a principle, a timely manner. So once people have been alarmed, and they are in a position in which they can start moving out of the area of risk, we are putting a whole series of measures to try to make sure that this is done in an appropriate way. Now, this is what brings me to the next level of language that we tend to use in fire safety, which is the language of the surrogate. We never explicitly describe what we are trying to quantify. What we do is we use surrogate variables. So let me try to explain that. A very commonly used surrogate variable is the concept of maximum egress distances. So what is a maximum egress distance? It's actually nothing real. A maximum egress distance is a creation that represents, in terms that an architect can understand when they are designing the layout of a building, a particular problem. So let me try to explain what that particular problem is. So if you have a building or a compartment, there's an opening in here and you have a fire. What is going to happen is that fire is going to produce smoke, and the smoke is going to start accumulating at the top of the compartment. If you have people in the immediacy of that fire, once the smoke detector or the temperature detector has activated, these individuals are going to start displacing themselves. Okay? And we can argue that there's multiple stages to that displacement. There will be what we call a pre-movement time, which is the period where people gain awareness and they realize they have to move, so there's a delay, an initial delay. Then they're going to start moving, and they're going to move at a certain speed, which is going to require them another time to be able to get to a safe place. Okay? And those times can be accumulated. But in essence, what we're really talking about is an evacuation time. We're not talking about a maximum egress distance. The distance is a surrogate, is velocity times time. I know what the velocity is going to be, and therefore if I multiply by the time, then I get this distance. But this is where the big assumptions come in, because in reality, a maximum egress distance could be infinity. Why it could be infinity? Because if I put a massive extraction system in here, and I take all the smoke out, and I have an absolutely infinitely efficient suppression system, I will get rid of the problem, take all the smoke out, and nobody has to move. Okay, so I have made my maximum egress distances infinity, because there is no need for people to move. As you know perfectly well, another way by which I achieve this is by creating compartments. If I box the fire, then I can get people out of here. I can put a barrier that prevents the smoke to come out, okay? And that effectively, once I've crossed that barrier into a safe space, I am safe. And the moment that I am safe, then I have the capacity to stay there forever. This is the principle behind stay put, that you can actually stay there because you are protected by the compartment that is going to enclose the fire. Okay? So in principle, it is a time that we're talking here about, and we're not talking about a distance. The distance is the surrogate. And these are the kinds of decisions that we make when we translate the information so that we can present this information to an architect, so an architect can design a layout. But of course, there's a lot of embedded assumptions. The first embedded assumption is going to be, how long do I need to get people out, but also how long do I have? Because this fire is going to grow, and it's going to grow at a certain rate. The rate of growth is going to be dependent on what materials I'm going to be using in the room. The rate of growth is going to be dependent on the size, nature, characteristics of the compartment, and it's going to be dependent on other measures, in other words, other dependencies I am putting into the system. So in principle, what I am doing is creating a situation by which I have an available time, and that's the time to reach untenable conditions. And that available time, which I'll call the time of the fire, okay, has to always be related to the egress time. So if the time available is smaller than the time that I need, then I have harmed the occupants of this compartment. But if the time available is actually much, much greater than the egress time, then I have fulfilled my objective of having these individuals remaining unharmed. So in essence, when you think about these things, what you realize is that a lot of the uncertainty that happens in these discussions about terminology, like maximum egress distance, is not necessarily related to the calculations that people are making, and it's not necessarily related to the actual concepts themselves. It is related to the assumptions. Because the reality is that if I double the height of this compartment, okay, which is part of the assumptions, this value is going to change drastically. So if I fix this maximum egress distance, what I have fixed is a list, a very, very long list of assumptions. So we can spend hours and hours arguing about whether it is 9.5 or 10.1, and if we don't list all the assumptions, the conversation becomes meaningless. And this is why it's so important, once again, to be absolutely explicit. And if we are not explicit, we have to recognize that all those participating in the dialogue will have not only a common language, but a common level of competency. Because only if they have the same level of competency and they can speak the same language, they will be able to interpret without being told what is that very, very long list of assumptions. And this problem manifests itself pretty much everywhere in the design of a fire-safe building. So this is sort of an initial example that I feel serves to illustrate to some extent the process. So I'll continue going through the different measures, and I'll try to bring other examples to bear. So once we have allowed people to be aware that there is a fire, then we expect them to move out of the area of risk. Now, we are going to play with this idea of maximum egress distance, or the comparison between the required safe egress time and the available safe egress time. We're going to be playing with this by creating a different layer of measures, which is the compartmentation. So if I deem that the whole path to a safe place is too long, then I want to break that path, creating a number of redundancies that enables me to protect people at each stage of their motion. So in essence, I set people to egress once they understand that there is a fire, and then I introduce elements of a compartmentation. Now, the compartmentation in a building like Grenfell Tower has fundamentally two purposes. One is to contain the fire. In other words, it's basically boxing the fire so the rest of the units are unaffected. And the second is to protect the means of egress, to enable at all stages people to move into a safer place. Now, we are going to consider, for example, what you see here in yellow, a first level of compartmentation. And that first level of compartmentation, that you can see in this diagram, will have certain characteristics that help protect that corridor. Now, this is, again, when we recognize what the assumptions are. So we know that that compartmentation has vulnerabilities, and those vulnerabilities are very clear. The door. The door is going to open, and the moment that it opens, it might potentially allow smoke. The door by its nature might not have the same capacity to control the fire or box the fire as the walls, so I know I have a weak point. So we know perfectly well that we can put other complementary measures, like putting self-closing mechanisms, but we know that those, again, are very vulnerable. Those self-closing mechanisms are going to fail. Those self-closing mechanisms are inside the unit, so they have to be maintained, and they have to be maintained with many times little control over how they're being maintained. So we know that these are vulnerable points, so we introduce redundancies into the system. So this is the point where we put a second level of compartmentation. So again, we have a second fire door. Now we have two layers. We're only requiring people to move out of that corridor into the next level of safety. which in this case becomes the lobby. And again, I'm going to have not one door, but now I have two doors that need to fail. So I've created a level of redundancy. And I've created a level of redundancy to enable a safe egress of individuals. Now, there's another need for redundancy, which is I have to establish how long people are going to be in each safe space. So if I think of the corridor of that unit, it's going to be a few seconds. But if I think of the stair, we recognize that if you are in the top floor and you have to descend the entire building, the period is going to be very long. So the stair will require another level of redundancy. So I'm compartmentalizing the stair in such a way that I've added an additional level of redundancy that protects my means of egress, making the stair a safer place than the lobby, and making the lobby a safer place than the hallway of the unit, and so forth. So I've introduced the concept of redundancies to make sure that my systems work. Now, many times we find that we get into a position in which we have created a dependency. Because the dependency that we have here is that if the lobby gets compromised, you cannot get to the stair. So you've created naturally a dependency. So you have to find a way to try to compensate for that dependency, and this is where you introduce things such as smoke management. And I'm going to use smoke management as an example, because I know you've heard in Monday and Tuesday a lot about smoke management, so I can allow myself to explain using that as an example of how you introduce this other level of redundancy and how the dependencies start piling up as I change the nature of the redundancy. So in principle, that fourth level of redundancy is there to resolve the dependency between lobby and stair, and but also as another layer of protection to the system. So now I have 4 levels of redundancy. So if I think about how we can move a flow. So let me just take a pipe. So if I just take a simple pipe, okay, we can all recognize that if I take a piece of paper and I push the air, wind is going to be created. What that paper is producing is a pressure on the flow, and the pressure induces a velocity. In a similar way, if I'm standing in the street and wind hits me, I'm going to feel the pressure of the wind. So there's a very clear relationship between velocity and pressure. The pressure is the force that creates the velocity, and the velocity, once it hits an object, can be reverted back into a force or to a pressure. Now that relationship basically says that the velocity is going to be proportional to the square root of the pressure. And that relationship is intrinsic to the way in which hydraulic systems work, to the way in which smoke management works, and all these different types of systems. So the velocity, once again, becomes a surrogate, while the pressure is the one who is driving the problem. So the velocity is a result of having an appropriate pressure that creates that flow that is going to move the smoke away from one place and put it in another. Okay? So if I have a system like this, where the flow goes in one direction, all that I need is to create a pressure here, 1, that is greater than a pressure here that is 2. So if P1 is greater than P2, then what happens is I introduce a velocity. And that velocity is a function of the difference between the two of them, so delta P is actually P1 minus P2. Okay? Now, the problem with this type of systems is that velocities are much easier to measure. So if I want to design a system and I want to make sure that it works, it's going to be much more difficult in a lobby or in a unit to start measuring pressures. So what I'm going to do is create a surrogate. Okay? But the problem is that what drives the problem is not the surrogate. What drives the problem is the pressures. So this pressure is the one who is going to determine the flow, and that's what's going to determine if I can extract the smoke. So what happens if I change the parameters? Now, let's go now to a building. So you are in a building, and you have a set of lobbies, and you have a stairwell. Okay? And you're going to have floors. And you might have a fire here. Okay? So this particular fire, because of gravity bringing smoke, hot smoke up and trying to push it away, this fire is going to create a pressure. That's the pressure of the fire. Okay? Now, then I'm going to have a duct. And that duct, because this is going to be hot smoke, this duct is going to have a temperature of the smoke that is greater than the temperature of ambient. In other words, because the hot smoke is hotter than ambient, there's going to be a force that is going to push the smoke up. So in this direction, I will have a pressure of the smoke. And this is plus. It goes in that direction. But the size of the duct determines how much friction I have, which is going to create a pressure that is going to go down. And that is going to be the pressure of the friction. Okay, but that's negative. Okay? Now, if I have a door that is open, that is going to create a pressure. If I have two doors open, that's going to change the game. Now, what gives me the velocity, the surrogate? It gives me the balance of all these pressures, because at the end, what I want to see is what is the net, the pluses minus the minuses. So I want to make sure that I understand what is the net to be able to understand what is the flow. So the flow, when I say that it's 2 meters per second, the one thing that I don't realize is that those 2 meters per second assume a typical pressure of a fire of one compartment of the size of a typical fire in a unit. Okay? So if I'm making that assumption and I'm designing for 2 meters per second, then I need to be clear about the fact that that is the assumption. Because what happens now if I have a fire that engulfs the entire building? That fire is going to create a huge delta P, a huge pressure difference that is infinitely bigger than this one. And therefore, what is going to create is an imbalance on my system that now is dominated by what is the controlling mechanism. So the system inevitably is designed for a set of assumptions. And those assumptions need to be perfectly clear. And if those assumptions are not perfectly clear, arguing about whether the system will work or will not work becomes a futile exercise, because it is the assumptions that determines the performance. And I might design a perfect system to work for a certain set of assumptions, but I need to be perfectly clear that that system is going to work in a different way if those assumptions fail. Okay? So in principle, what I have is a system that was designed for a set of assumptions, and among the set of assumptions is that the delta P that is created by the fire is the fire of one unit. And if I fail to guarantee that, then I have no guarantee how the system is going to work. Now, not only is it designed for that, but it's also designed to enable firefighter intervention, because if you actually have the fire in the top floor and you have the firefighters coming in from the bottom floor, you're basically pulling fresh air into the stair. Now, if you have people opening doors in multiple floors with smoke, you might end up in a situation where your hydrostatic pressure, or the pressure that is created by the temperature increase, might end up actually bringing the smoke into the stair or into the lobby. And all these variants are a very fine equilibrium where all the pluses have to be compensated for the negatives to give you a net. And in which direction that net goes is a function of what are the pluses and the minuses. And if you introduce this type of dominating factor, then obviously what is going to happen is that the system is going to perform in a way that is different to what it was intended. Okay? So as you can see, assumptions are very important. And certain assumptions are going to take a more important role than others. And we have to be extremely careful about this. Because, for example, we're going to make assumptions about compartmentation. And those assumptions might not be correct. Nevertheless, we have 4 levels of redundancy. Okay? But we might be making assumptions about a smoke management system. Well, we know we have no redundancy because if the fire exceeds 1 unit, the delta P changes and your smoke management system is going to have a different performance. Okay? So these are the kinds of nuances that are necessary if we really want to understand a fire safety strategy. So at the end, the objective of introducing compartmentation and smoke management is to deliver a safe area. Now, the safe area could potentially be the stairs, and if you have an egress strategy that requires to evacuate people, you will have to maintain that safe area for a very long period of time until people fully evacuate the building. Okay? But if you're going to implement a stay-put strategy, and this is something that becomes to some extent contentious, if you are going to have a stay-put strategy where your safe area is all the spaces occupied by all the other occupants of the building, then you just simply cannot allow for fire spread. Okay? Now, people are going to argue, and this is going to be explicitly said many times, that an absolute statement of no external fire spread is unachievable. This is going to be the argument on an endless basis. Now, I'm not necessarily disagreeing with that. It might, making absolute statements might not be necessarily appropriate, but you can modulate those statements. You can say that the objective is no fire spread, and you can modulate it by saying to a certain probability. You can modulate it by making a statement that no fire spread, but if fire spread happens, here is my plan B. My contingency, this is how we pick it up, the redundancy. So we can put all this, but we can still set the objective as being no fire spread. And we can qualify it according to what we need in very different ways. Because in essence, by principle, if people are going to be remaining in other areas and there is no contingency plan, then in essence, by principle, no means no. And there is no way about it. Okay, because keep in mind that it is our acceptance that occupants are not responsible for understanding fire safety. So the decision making that will prompt them, to leave a unit if they come to the conclusion that the risk has reached an unacceptable level, it is a decision that we cannot impose on them. So we have accepted that we are delivering the safety, and we are not expecting the occupants to make those decisions that are informed decisions. So, in essence, this is the principle behind no external spread. Now, obviously, if we have a stay-put strategy, even if we are evacuating people, we would like the structure to remain in place. Collapse of buildings is never an unacceptable outcome. So the way in which we set the objectives for structural performance is by saying that the structure will have to withstand the burnout of the fire. So even if there is no intervention, when all the fuel is consumed and the fire dies on its own, the structure should still be standing, which is effectively the case of Grenfell Tower. So in principle, that enables us also to have a level of redundancy to our egress, because we have plenty of time from a structural perspective, and it allows for fire brigade intervention without the risk of the building falling on them, and it enables also the possibility of extending, our evacuation time to as long as it is necessary. So finally, we have the fire brigade, and the fire brigade obviously plays a role. And again, there are the actions of the fire brigade that we need to take into consideration, but also we need to understand what is the objective that we set for them. So when we look at the protocols of the fire brigades, the objective that we set for them was to suppress a 1-unit fire, as they did in the case of Grenfell Tower. Okay? So in principle, if we don't set those objectives correctly, then we have the potential of misleading the fire service in a direction in which they will not be effective in their activities. So there's an element of explicit information that needs to be transferred, which is what we are requiring from them. Now, documentation obviously is essential because the training of the fire service is very different to the education of a structural engineer or an aerospace engineer or a mechanical engineer. So we're going to have different languages, we're going to have different levels of competency in different areas, and therefore the communication becomes fundamental. So in essence, that gives you a sense of how you put together a fire safety strategy and how dependencies and assumptions become extremely relevant. Now, once we have the fire safety strategy, there has to be an element of transparency in its assessment. So somebody has to be able to come and make an appraisal and assess if that strategy is actually going to work in time. Things might deteriorate, things might change, modifications might be made, and we have the need to conduct the fire risk appraisal or assessment. So that's an integral component of the process to make sure that the system as designed continues to perform in time. So I'm going to use as an example the newly produced PAS 9980, to try to explain how we have dealt with this concept of appraisal and how we are leaving to the competent professionals an enormous space for interpretation that we need to understand how that enormous space of interpretation correlates, with competency. So if I just take one statement, from the document, you can immediately realize that statement in itself carries a very significant weight in numerous forms. So basically, the statement says that the only way external fire spread can be prevented in its entirety is to build a building out of entirely non-combustible materials and not have any windows or other openings in the external envelope. Now, let me try to explain that this statement carries an enormous set of assumptions. Okay, it is based mostly on a document from 1966 by Langdon and Thomas and Law, and where they did a series of tests where they actually showed that the expectation is that when you have a building, and this will be different floors of the building, and you have a fire here, the expectation is that the fire will end up here. But they demonstrated that the reality is that actually, under the circumstances of their tests, the reality is that the fire actually went in. So they conclude that expecting that a fire cannot ignite the floor above is an unrealistic expectation given the circumstances that they run the tests. Now, I am not going to disagree with this. I actually think it's a perfectly valid argument, particularly if the window is open. The window is obviously a barrier that will slow the penetration, but eventually the window might fail. But if the window is open, you have a direct barrier. Okay? Now, that's the first assumption, is that effectively we're working with the configuration that they used. Now, there were further studies in Canada that actually complemented this. So the configurations are more than one, but the reality is that they are the assumption. It works for these configurations. Now, the next assumption is the difference between smoke migrating into a space and actually having ignition. To have ignition, you need a sufficient amount of heat to reach the materials in here, which is a much, much more onerous condition than having smoke penetrating. Now, in principle, this is an appropriate statement to make, but you have to disclose all the assumptions that go in there, because the reality is that we also all know that I can change this problem. And if I start extending this balcony with non-combustible materials to the point that this flame never makes it to the end, okay, then I can actually design a building with windows that actually works, because the flame will never get into here and the smoke will go up. So by the time it's blown by the wind, it's so diluted that it doesn't produce any harm. So in principle, I can design a building with windows. Okay, so that's not the limitation. Now, even the use of combustible materials. Well, I can allow myself to put combustible materials here, because the flame will never have enough heat to ignite it. Now, obviously, in the tests that Langdon, Thomas, and Thomas and Law did, their protrusion is 2 feet, and they found 2 feet as being insufficient. And I understand that, because it's not enough to divert the flame completely away. But when you translate this into a statement that says that to be able to design a building for the no spread condition, you have to design it made out of totally non-combustible materials, and also that it has to have no windows. There's 2 things that you're doing. One is you're not presenting your assumptions, and 2, you're implying that we have to allow for fire spread. So that's the implication, that given that you cannot avoid it, you have to allow for fire spread. Now, that in combination with the use of other types of language very rapidly brings you to a position where you realize that interpretation, knowledge of the assumptions, understanding of the dependencies, knowledge of the conflicts becomes absolutely essential to be able to answer the questions. Because what you're saying is that the building, for the building to be considered acceptably safe, you have to define what acceptable means. Then we have now switched from a condition of no spread to a condition that implies time. And they say the time required for fire to spread externally from one compartment to another, or from one story to another, needs to be sufficiently long. In other words, I need to be able to quantify the spread rate or the failure time of the system. And somebody has to do that in an explicit way. Now, that is going to require not only understanding combustibility, but it's going to need to understand the thermomechanical behavior of the system, because these systems are going to be heated, and as they're heated, they're going to deform. And all this needs to be understood. All that now, again, is being piled again and again and again. And then it is combined so as to allow for safe escape and the intervention of the fire and rescue services. How do we communicate to the fire and rescue services what is the acceptable spread rate if we don't write it down? How are they going to understand that they should expect a 4-story fire within 10 minutes of ignition if we don't show them how we calculated things, how we estimated things, what assumptions did we make, and what are the dependencies and conflicts that are potentially there? So I can continue to read every single one of this, but I think there is truly no point, because they all go more or less in the same direction. Not unduly harmed. What is the definition of unduly harmed? Prevented from escaping. What does it mean to be prevented from escaping? What is visibility? Is it temperature? Is it carbon monoxide? What is what we're talking about, and how do we quantify it? All these things, at the end, land into statements such as do not compromise the communal means of escape. And what is worst of all this is before those needing to use the escape routes. So if you think about it, this terminology, from my perspective, requires more and more to emphasize the competency of those individuals delivering this analysis, and furthermore, their capability to communicate in a way such that information gets transferred in a manner such that everybody can do their job. So at the end, we need to understand, what provisions are going to be put in place for fire spread. Because as we recognize, if we have a stay-put strategy, we have to find compensation for not fulfilling the requirement of no. So without stating clearly what are those provisions, then we have no guarantee that things are going to work correctly at the moment of the event. What is tolerable, what is acceptable, how are time and firefighter capabilities quantified, all the things need to be explicitly addressed. What is unduly harmed needs to be explicitly addressed. And how do you guarantee that escape is viable? You have to have a plan. There is no point in having a situation unfold in front of you if you don't have a plan on how to deal with that situation. Now, a further problem that tends to happen is that without the benefit of hindsight and the knowledge, of what happened in Grenfell Tower, I wonder how a designer will answer the question if 4 levels of redundancy were sufficient. Because in principle, I could use every single one of these words and argue with perfectly valid arguments that for this particular building, 4 levels of redundancy was sufficient to allow for the flame spread that we observed. And I could actually even argue that the fire service should have had a plan, and it was their fault for not having a plan to intervene in that case. And I could make many, many different arguments as a designer to justify designing this building exactly the same way as I did on the first place. And I think this needs to be very, very, very clear, because in many ways, you will say that it's professional responsibility, moral and ethical behavior, but at the same time, it is competency. Because if you don't understand the consequences of your actions, many times you might think that a problem is much, much simpler than what it is. And I do think that this is not a simple building. Many people will claim in a simple problem like this, we do not need the appropriate documentation. I'm sorry, but this is not a simple building. This is a very complicated building by the mere fact that we allowed external fire spread. So, as you can see, even when you're doing an appraisal and assessment, you need to have not only a very clear idea of what you're aiming for, but also you have to have the level of communication and competency that is appropriate to the language that you're introducing in your documentation. So, which brings me to the concept of the fire safety strategy and what are the basic components that a fire safety strategy should have to be able to allow me to start thinking about the performance of a system. Because as you can see, I haven't even started talking about the performance of an external building envelope. All I have done is set up the stage, and I still haven't got to the point where I can actually define the performance. So the first assumption that we make is that there will be a single event, a single fire, which inevitably, the moment that you have multiple fires in multiple units, that main assumption is going to break down. Now, I'm going to implement a detection system that is going to enable me to try to establish when people are going to begin the process of egress, or they're going to be made aware that there is an event. And then I'm going to put the 4 levels of redundancy associated to compartmentation to try to achieve the objective of guaranteeing a safe area. That safe area could be the full building if it's a stay-put strategy, or it could be the stairs if I'm going to enable an egress strategy, and I need to resolve through the smoke management process the conflict between the lobby being a preamble to the stair. Okay, so basically I've more or less handled all this. And then I have the no external spread. And I know that that no external spread is going to underpin a number of different things, and therefore there are many dependencies associated to the no external spread. And then I have the structure, and the structure has to withstand the fire, and eventually that gives me the rest of the building as a safe area, and that also enables a stay-put strategy. So now, if you think about it, that is delivering building safety, is the building doing its job. Okay? Now, that can fail, and we recognize that, and we have an extraordinary redundancy, which is the fire brigade. So the fire brigade will come in and try to address any issue that actually escapes the design premise by which this building was to deliver the safety that we're aiming at. So on top of that, we have to add proper building management, because many times provisions for that. We have to add maintenance, we have to add inspections. And all these things guarantee us that through time, the building is going to continue to perform. Okay? So if we think about it, detections, they have redundancies. In most units, we will put multiple detectors, and those redundancies are there to try to make sure that if one fails, others will pick it up. Obviously, with compartmentalization, as we've seen, compartments have multiple levels of redundancy because we recognize the weaknesses and we recognize the dependencies and the potential conflicts. Now, the fire brigade represents a redundancy to the whole building operation, and we've put that in place. Now, in the case of the structure, the way by which we achieve the necessary robustness is by using an assessment criteria that is effectively very conservative. So we basically design structures to perform under the worst possible fire for the longest possible period of duration, which is burnout. And by making the test a bounding test where nothing can get worse than that, we've added a massive set of safety factors into structural behavior. Now, we can criticize the method a lot, but the reality is that in practice, we have implemented a very robust approach, which is increasing the factor of safety to a magnitude that is extremely large, because we recognize the dependencies on the structure. So we've done that appropriately. Now, when it comes to the no external spread, and we start looking into the dependencies, we realize that no external press bypasses compartmentation and has the potential, as I explained, to disable smoke management. So in principle, that's a very strong dependency that has already killed 2 levels of my problem. Now, there's a dependency on the structure because the assessment method that we use that is so robust for structural analysis is an assessment method that is predicated on the rest of the building being cold, so the loads can be redistributed. So in principle, there is a dependency on structural behavior that we need to recognize. There will be a dependency on what are the safe areas, because if we are allowing the fire to move away from the space, we are effectively changing what is a safe area. And so we need to take that into account. And of course, there's a dependency with the fire brigade, who in principle has a protocol to fight a fire of a certain nature that could be completely changed, and they will be presented with a fire that is completely different. So as you can see, we have created a massive amount of dependencies on the building envelope and its capacity to prevent the spread of a fire. Now, we have no redundancies. They're only dependencies. And the problem that we have is that on top of that, we have a conflict. Because the moment that we give priority to the fire brigade to fight the fire, we recognize that if the smoke management system is not working as intended, then the potential for having smoke in the means of egress and propagating itself to a number of different places is very high. So just by the mere operations of the firefighters opening stair doors to put the hoses and fight the fire, you're creating a potential conflict, because when we had the 1 unit fire, we had a stay-put strategy that created a sequence. The people in the unit evacuate, 1. Once that's terminated, firefighters fight the fire, that's 2. And then people can migrate out of the building. So in principle, we created purposely a sequence, and we assume that sequence will be respected. But if this fails, then we are creating potentially a conflict, because we have to evacuate people while intervening in fighting the fire. So we need to be able to recognize these things. Now, a fire safety strategy is not only listing all the things that you did. is primarily listing what your assumptions are, what your dependencies are, and what your conflicts are. And if you're not explicit about all these things and make them extremely clear, you will become the victim of words such as adequate, useful, and all these things that in principle are part of the understanding of the problem. Now, as I say, buildings last in time, and buildings are complex systems, and they require people from multiple disciplines to intervene, and therefore communication becomes essential. And that's why, having the appropriate explicitness in all these things is absolutely fundamental. So, if that is okay, Mr. Chairman, I have 2 more slides.
Yes.
And I would like to go through before we take a break.
Of course. Now, you indicate when you think it's a convenient time.
Okay.
I think if we get close to 11:30, the stenographer might like a break anyway, but...
No, it will take me probably 10 more minutes.
That's fine, of course.
Okay. So then we have to move into the concept of performance objectives. So we need to now be quantitative. Now is when I start talking about how we define performance for the building envelope in as much as for everything else. And in some cases, it's actually quite easy, but in other cases, it's very, very complex. So the detection, in the case of the detection, establishing performance of a detection system is actually very simple, because an ideal detection system will give you immediate warning instantaneously. So if the time to detection is 0, you have the perfect detection system. So the technologies will aim to 0. That's the performance target. The only thing that slows them down is that you have a lot of nuisance alarms. The more sensitive you make your detector, the more nuisance alarms you get, and therefore the less people are going to be prompt to react appropriately to the smoke detector. So that's pretty straightforward. So technology, as it evolves, what the technology is trying to do is target 0. Very simple target. And technology is dedicated to try to minimize nuisance alarms so that they can bring the detection as close as possible to 0. Because if you make detection 0, then you can ignore that part of the problem, and what people do is what really matters. And that's the only times that actually matter. Now, other aspects that you need to take into account, you have to put sufficient detectors, because the smoke has to get to the detector. So you're going to place the detectors strategically to make sure that that time gets as close as possible to 0. But as you can see, I have a very simple and straightforward performance target. Now, with compartmentation, again, I have a very simple performance target. Do not allow fire or smoke passage until the burnout of the fire. Now, I can devise a method to establish that, and I can devise failure criteria that enables me to address that particular target. So these are the easy ones. So defining compartmentation and defining detection as performance targets are actually quite straightforward. With external fire spread, the problem is a lot more complicated, because you have this apparently impossible target of cannot allow a flame to spread. Okay? That, of course, is a difficult target to achieve, particularly in modern systems that are so complex. At the same time, the system should not allow smoke to migrate. So deformations and things like that that could allow the passage of smoke could potentially be a problem, even if a fire doesn't ignite in a different place. And of course, the system cannot ignite and spread a flame when solicited by a fire external to the building, which is the one that we understand better, which is a fire that is in another building and produces some heat that is going to ignite the facade. But the performance criteria then start becoming a lot more complex and much more difficult to quantify. With the structure, again, is simple. We are basically going to require to sustain no failure according to a predefined failure criteria and according to a predefined bounding test. And with the fire brigade is extremely complex, because we recognize that the emergency response is a response to building failure, which is the task. Okay? Then we start introducing things like foreseeable events, because protocols for firefighting need to be defined, and therefore foreseeability needs to be assessed. And we have to achieve an acceptable outcome. And once again, we run into the same problem of what is an acceptable outcome. We can always take the position, that firefighting is such an impossible task in nature that any outcome is acceptable, but we recognize that that is potentially not an acceptable approach. Or we can establish clear performance criteria of this is what you need to achieve. And again, that becomes quite difficult. So we need to be quite careful on how we use this redundancy to the system in a way such in which we set performance criteria that are appropriate to the capabilities of the fire brigade, but they don't exempt them from their duties. So in essence, once I have those performance criteria, I find ways to target them. And again, in the case of the detection, I have to quantify the activation time, so I have a standardized test that I use to characterize and calibrate all smoke detectors that enter the market. Very, very straightforward. So in the case of compartmentation, this is what brings the concept of fire resistance. So I have a test, and that test delivers a fire resistance rating, which basically tells me for how long, according to the test, the system will fulfill its functions. And I can classify these buildings in a fairly simple way. In the case of external fire spread, things again get very complicated, because there's issues of flammability, but there's issues of thermomechanical performance of the system. In the case of the specific building, because the interactions between the components are going to be critical to the way in which the system behaves. So it becomes a system performance. And the system performance pertains to the building you're trying to design. And therefore, it is really fundamental that this is looked upon in the context of the design that we are producing. And in essence, the objective is to support the fire safety strategy. So whatever external building envelope we design, it has to support the fire safety strategy that we have implemented. This is why, for example, when we design facade systems for offices, where we have sprinklers, we have an evacuation strategy, we have complex smoke management systems, we might tolerate certain things that we will not tolerate, for example, for a residential building where we have none of those features. So in many ways, the concept is that we have to support the fire safety strategy, but now we don't have a test. We don't have a target. It's not an activation time. It is something that is much more complex than that, and it becomes a system performance. And again, with the structure is fire resistance again, so no need to talk about that anymore. And with the fire brigade, we tend to resort back to the statement that they have to perform according to what is being requested from them by Fire and Rescue Services Act of 2004. Whether that is clearly defined or not, that's a different story, but that's what we are charging them with. So I think that this will be a good moment for me to stop, if that's okay.
Yes, certainly. Well, thank you very much. All right, well, we'll stop there. We'll resume at 11:30, if that suits you.
Okay.
And I think I should say to you, as I've said to every other witness, please don't discuss your evidence while you're out of the room with anyone.
Perfect. Thank you.
Right? Thank you very much. Would you go with the ushers then, please? Okay. Thank you very much. Ms. Grange, 11:30 then. Thank you. Would you ask Professor Torero to come back in, please? All right, Professor. Well, we're ready to carry on when you are.
Okay, thank you very much. So, in the second part of the presentation, I am going to focus on actually the quantification of performance for external facade systems. And, before we look at the object in itself, we need to try to understand to some extent, or at least to a sufficient extent, how the different physical processes are going to interact, with the system in itself. So the example I'm going to be using to try to provide this explanation, it is the simplest possible example, which is just simply a combustible material and how a fire will spread, within a combustible material. I will move on then to look into more system behavior aspects of it, but initially to try to describe the different phenomena, I want to use a more idealized and simple scenario. So, in simple terms, a facade system is going to be subject to two different types of solicitation. If you look at the image in the left, you will see the growth of an internal fire. So this is an internal fire that starts burning in the interior of the unit and is going to deliver a heat flux, an amount of heat per unit area, to the structure. Now, the structure obviously comprises of the ceiling, the floor, the internal walls, but also comprises of the external system. So the external system is also going to receive this solicitation. Now, if you look at the diagram above the photograph, you will see more or less the magnitude of the heat that you receive. So in the highest point, which is in the center of where this fire is, you will find that you get numbers of the order of 500 kilowatts per meter square. Now, you can see 500, 400, 200, 300 as you move away from the source of the fire. Now, what this shows you is that the fire in the interior of the compartment tends to be much more onerous than the fire in the exterior of the compartment. Now, normally for the wall, the internal walls, the ceiling, and the floor, we will address this through the process of fire resistance. Now, from the perspective of the external components of the wall, we will not address this. We will make the assumption that the external components will not require any fire resistance, and therefore they're not addressing the solicitation from the interior. Now, that in itself is a limitation and a very, very strong assumption that we're making, because effectively it assumes that in the intersection between the external part and the internal part, there will not be a potential gap that gets formed. Now, this is I think, in many ways, a legacy of the past, because we used to have systems where you had a floor slab, and we used to sit and hang components out of the floor slab. So inevitably, by assigning a fire resistance to the slab, the interior fire was protected, and any solicitation that came in this direction, any heat flux, will have to breach a fire-resistant floor before it could get to the compartment. Now, that is going to change dramatically when you have a system that is pinned by a connecting element that you're going to fill with something in here, because you're going to have the same solicitation, but this time the performance is going to depend not only on the properties of the infill, but how all these things move together. So all of a sudden, you have moved from component performance, which is quite easy to establish, to a system performance, where is the relationship between the building, the external envelope, and the connecting elements that will determine what will happen. Mm-hmm. This, by definition, is a much more complex system, and that currently remains fully unaddressed. So That will be the internal aspect. Now, the external aspect, as we can see here, results from the acceptance that the building envelope will fail to the outside and will project a flame that, because of buoyancy, will bring flames and hot gases up. And that's the second photograph that you see in the middle. Now, this particular projection of the flame can be characterized by a region where the flame is going to exist, which is the flame length that I call LF, and is going to be the heat coming from this flame, but it's going to come from the external solicitation. Now, temperatures on the outside of a compartment tend to be much lower than the temperatures on the inside of the compartment because air tends to dilute the heat. Buoyancy brings a lot of air that cools down the smoke, resulting in a much lower temperature. And you can see from the plot that I have in here. Now, the bottom part of the plot represents the edge of the window. And as we move up, we're moving up away from the edge of the window towards the top of the flame. And we can see, if we follow the red curve, we can see how we start at about 60 kilowatts per meter squared, and we descend as we move away to values of the order of 10. So you can see that this solicitation is very different. So now we have a much lower heat flux, and that much lower heat flux is a decaying one that is going to basically shrink as you move away. So if you get far enough, and this is a concept of protecting by means of a spandrel, if you get far enough, you will get to such low heat fluxes that you might have the capacity of preventing ignition. Okay? I can achieve that by putting a spandrel. I can achieve that by putting a projection. So basically, I can move my endpoint far enough so that I'm low enough. Now, obviously, as I depicted in this diagram, that can be very far. So it might be impractical. And we need to take that into consideration. But nevertheless, it's something that we can play with. Now, I plotted two lines. I plotted the red lines and I plotted the blue lines. The dotted lines represent the range of values that were measured, and the blue lines and the red lines represent different scenarios. People have done many studies on external plumes and the heat fluxes, and what you can see is that in the worst case scenario, you might reach a peak value that is not 50 or 60 as you have here, but it might reach up to 100 or 120. So those are the greatest values that people have measured. So it starts at about 100, 120, and then it will decay back into about 10. Now, depending on what materials you're using, depending on the geometry of the compartment, depending on the openings of the compartment, the things will change. The decay will be more pronounced or less pronounced. The peak value will be higher, will be lower, but the physics is more or less the same. Now, the additional component of the process is the external heat flux, which is what I called QE in the bottom. Now, that's any heat that can come up from either another burning building, as we can see here, or it come up from another surface that is burning. So once you get multiple ignitions, you can have heat from one flame feeding onto the other, which is what tends to happen once a fire develops, that you start getting several areas that are burning and they're cross-feeding each other. So in essence, if you look at the diagram on the right, you will see that you have two sources of energy: the external heat flux that comes from the outside and the heat flux that comes to the flame, from the flame. Okay? Now, if these sources of heat flux are capable of igniting the material, then the flame will spread. Okay? Now, this is a very important aspect of the problem, because the capability of a heat flux to ignite a material depends on two fundamental variables. The first is that here is the material, here is your flame. You have to have sufficient heat. So this has to be big enough so that it's capable of igniting a material. Just to give you an example, if you put a desk in the sun, it will not ignite because the heat flux from the sun is too low. So it can warm up, but it will never reach a point where it starts degrading and igniting. Okay. Nevertheless, if I make it big enough, then it could potentially ignite. Now, the flame is a physical space. So that flame is going to provide heat only to a certain region. So the flame cannot heat very far away. It will only heat up a certain region. And this is what I call LH. So this is the heating length. Okay? Now, this here is the burning length. So it's the area of the material that is already burning. So this is already burning. This is what is providing fuel so that the flame can continue to exist. The flame now is combusting with the air that is feeding it and is providing a heat that is heating up this heating length. Now, what happens if the flame starts shrinking to the point where the burning length is now the same size as the flame? Then the flame has nothing to heat, and the system will stop spreading. So the condition that tends to lead to no spread is a condition where LH is approximately equal to 0. In other words, my amount of fuel starts shrinking, so the flame becomes shorter to the point that it cannot heat anything beyond what the burning length is. Eventually, this material that was burning will consume itself, and once it consumes itself, then it will stop burning. Now, while I have a heating length, while LH is greater than 0, in other words, I have an area that is being heated, there is a propensity for the flame to spread. Now, this condition of LH equals to 0, okay, is really a very simple representation of a much more complicated problem. But in essence, gives you the physical basis of the concept of no spread. Now, you can achieve LH equals to 0 in many different ways. So, for example, you could potentially insulate to try to prevent the heat from getting there. So you are effectively, by other means, achieving the same thing. You can increase the ignition temperature to an infinite value by encapsulating the material with a non-combustible material, and you are achieving the same objective. So you can play with different measures, aluminum foils, ceramic renders, aluminum plates, all these different ways to try to create mechanisms by which you are bringing effectively this value to 0. The problem is that this is my very simple case of a single material where LH only depends on the relationship between the amount of fuel and the heat flux that comes from the flame. If I start creating concepts such as encapsulation, I start introducing other variables like mechanical behavior. And the moment I introduce mechanical behavior, then it is not the fact that LH equals 0, is that I am protecting the material by means of a mechanical system in such a way that I have created an equivalent system that renders LH equals to 0. And this is how I start building this complex form of behavior. So in principle, the idea is that the way in which a fire spreads is that I produce fuel, the fuel produces a flame, the flame brings heat flux through an area that is given by LH, and once the temperature of this reaches its ignition temperature, the flame jumps. Okay, and it jumps a certain distance, and that distance divided by the time to ignition will give me the velocity. Okay, and I have a flame spread velocity. Now, in essence, the concept in itself is a concept that we've understood since the 1970s. And there's a famous paper called Controlling Mechanisms of Flame Spread that explains all this, and it's a paper that dates from the early 1980s that summarizes work since the 1970s. Now, the application of this to the more complex systems is something that is a different story. That has, again, brought all sorts of other complexities that have made things a bit more difficult. So, in essence, the objective, if what we are aiming to is no spread, is to find a way by which we do not allow a preheating length that can enable the ignition and spread of the material. Whatever mechanism we use, whether it is natural when you have a single material or whether you introduce barriers to try to prevent this from happening, that is the objective for no spread. Now, if the objective is to quantify spread, then the problem is different. We allow spread to happen, and the only thing that we do is we measure how fast it takes to jump this length. So if it's going to jump, what I call a delta LB, so a piece of LB, if it's going to jump this amount, then I need to quantify the time that it takes for it to jump so that I can look into how rapidly it's spreading. So these are basically the performance objectives, and it depends on your fire safety strategy which one is the one that you're going to pick. If you have a stay put strategy and you're aiming at not spread, you will be looking into targeting your design to meet the no heating length condition. While if you are going to allow for flame spread, your objective is to know how fast. And so that you can create the entire fire safety strategy around a quantifiable and acceptable level of flame spread. So basically, the next step is to try to go back and look into what are the parameters that control this process. Okay? And the diagram to the left shows you a sequence of parameters that are going to influence LH and the flame spread velocity. So I am not going to go into the details of the different parameters, but I do want to explain a little bit the sequence because they are related to the way in which we test. So what we were discussing was that the material will produce fuel, and that's the MF on the left-hand side of the diagram. And the amount of fuel is going to depend on how big is the area that is burning, and that is going to be the LP. In other words, the term on the top is how much fuel is being produced, and the one on the bottom is how big is the area that is producing fuel. The bigger the area, the more fuel you're producing, the more combustible the material is, the faster it's going to produce fuel. So if you have, for example, a liquid fuel like kerosene, the burning rate, or this MF, will be very large. While if you have a heavy fire retardant material, the MF will be very little. Okay? And, but the second term, the LP, is going to grow in time, because as the fire spreads, you're going to have a bigger and bigger and bigger and bigger and bigger area that burns. So it is part of what needs to be calculated. So that is going to progress in time, and I need to be able to calculate that to be able to understand how rapidly the fire is going to spread. So the product of the area burning times the amount of fuel that is being produced per unit area will be the total mass of fuel, and that is the next term, MF, without the double prime. Now, you have now the fuel, and the fuel will combust, and it will have a heat of combustion, and that's the energy that is released per unit mass of fuel. So you have the two terms, the heat of combustion and the amount of fuel, and the two of them multiplied will give you the total heat release rate. So that's the amount of energy that the system is producing. So on the top, I have the amount of fuel that I produce per second, and on the bottom, I have the amount of energy that I produce per kilogram of fuel that I generate. If I multiply the two of them, I get the heat release rate, and that's the value of Q dot. So Q dot is a typical representation that we use for the heat release rate. Now, the heat release rate, in essence, is one of the most important variables that we address in fire, because in many ways, it is the first clear manifestation of what the fire is, which is an amount of energy that is being released every unit time. Now, that heat release rate is going to control the temperature of the flame, and it's also going to control the temperature of the smoke. So the two next terms that you have to the right will be the temperature of the flame and the temperature of the smoke, TF and TG. And it's also going to control the length of the flame. Now, this is very important because if you have a material that does not have a heat of combustion, in other words, is non-combustible, then your heat of combustion is 0, there is no heat release rate, and therefore you have no flame temperature and you have no flame length, and the problem stops. So the easiest way to prevent spread is by eliminating combustion. Okay? Now, if you are going to allow combustion to happen, then you have to continue now the process. And now you have to quantify how that temperature of the flame and that temperature of the smoke is producing a heat flux. And that heat flux is heating the material. You also have to be able to quantify what external sources you might have, and that's the term on the top, the blue term. And you also have to be able to quantify how the air, by flowing, because it's fresh air, is cooling the whole process, but also is driving the geometry of the fire. So this is why, for example, many times we choose certain geometries in the test. Why do we have the room corner test? We have the room corner test because that allows the air to come in a certain way that produces the longest plausible flame. And that is considered to be the most onerous case. In BS 8414, we have a corner. Why do we have a corner? For exactly the same reason. The air comes in a certain way that produces a flame that is the most elongated and therefore is considered the most onerous case. So I cannot ignore how the air comes in because the air is going to determine the geometry of the flame and therefore is going to be critical in me being able to determine if I have an LH or not. Okay? Now, the next row are the fundamental parameters that will control these things. These are properties of the material. And there's no need in going into detail other than just understanding that these properties are going to be controlling all these things. So the phi, the parameter phi, is what determines the potential of the flame to radiate heat. The parameter T infinity is the ambient temperature. That's the simple one. T ignition will be the ignition temperature of the material. The higher the ignition temperature is, the more difficult it is to ignite the material. The lower the ignition temperature, the easier it is to ignite the material. And K multiplied by rho multiplied by C is the thermal properties, and that's what we call the thermal inertia. A material that has a very high thermal inertia is very difficult to ignite and to spread. A material that has very low thermal inertia is very easy to ignite. So if I combine all the parameters up to LH with all the material properties to the right, I can eventually estimate the flame spread. So as you can see, then that flame spread, and that's the dotted line, will deliver how much area of the material is burning. And the faster your flame spread, the faster it grows, and the more exponential growth you get for the whole process. Okay? So they're linked, so there's a feedback loop in this whole thing. So as you can see, this is a complicated problem. And we need to be able to try to address this problem in ways that are tractable. But nevertheless, to be able to address these problems in ways that are tractable, the first thing that we need to do is to understand it. Once we understand the problem, then we can try to find a simpler formulation. Mm-hmm. Okay? That's the objective. When we go from the knowledge base into something that is practical or viable for people to be able to design and to be able to work, that has to be based on the fundamental understanding. So we need to take this problem in its full complexity and try to understand it. And once we understand it, we can come up with simpler methods of assessment. Okay? Now, as I said, I just touched on the complexity of the problem. And as you can see from the photograph on the right, that is a photograph of the Windsor Tower in Madrid. And the reason why I picked that photograph is because if you look at the columns, you will see the deformations induced by buckling. So you can see the magnitude of the deformations that you can have because these materials, these railings, are being heated. So we cannot trivialize to what extent mechanical deformations are fundamental in the behavior of the systems. And they need to be considered at every stage in the assessment of a building envelope. These are not simple deformations. These are massive deformations that can create enormous gaps, and they can create the possibility for penetration. Now, needless to say, on the left-hand side, I extracted this from a phase 1 report. You will see when we start adding all these components, and we have insulation, we have a composite system of aluminum and a combustible polyethylene material, you introduce a cavity in the middle, you start creating all sorts of different mechanisms that complicate the problem much, much, much further. So our need to understand gets enhanced. Now, this is a problem that I feel is very common, that the moment that we address a complex system in the area of fire, our tendency is to naturally resort to, let's do a big burn. So if we don't understand, we burn. And to me, this is really, really problematic, because extracting proper information from a large-scale test requires not only an enormous amount of proper measurements, requires a very clear understanding of the objectives and the way in which the test has been set up, but it also requires an enormous amount of competency to be able to interpret the results. And doing a large-scale test because I don't understand cannot be the process to be followed. You understand, you formulate the appropriate test, and if you need a large-scale test to fill the gaps of system behavior so you get the information that you need, then you implement the appropriate measurements and you deliver the test with the appropriate results that fill the gaps that you need. But we cannot use the large-scale test as a mechanism to compensate for our ignorance or incompetence, because all we're doing is creating a bigger problem that we are going to understand even less. So the forms of encapsulation will vary. You have fully encapsulated systems, as you will see in this case of A. You have partially encapsulated systems, as you can see in B, where the top and bottom are left open, or you can have one-side encapsulation, as you can see in C. And all these systems will behave in a different manner. So all these mechanisms are happening, all these mechanisms need to be taken into account, and all these mechanisms are part of understanding the problem. Now, if we can run this video, that will give you an example of one of the most important aspects of understanding. Is when we create a complex system, and this is an aluminum composite panel, you can see it clamped on, this is the aluminum composite panel, is clamped on one end, and this is a heater that is providing a heat flux against the aluminum composite panel. Is it running? So the moment that we remove the cover, it starts heating up. And what you need to observe is the failure mode. The failure mode of this will be at some point, the front aluminum panel will actually split. And we will stop the video at the moment it splits so you can see what happens. The moment it splits, then the aluminum is no longer attached to the polyethylene, is allowing the polyethylene to be exposed, which is effectively enabling the existence of LH. While the aluminum is attached to the plate, the aluminum is basically taking the heat, and therefore it's going to happen in here. So as you can see, if you look carefully at this area here, you will see how the aluminum plate has split. And the moment the aluminum plate has split, if you let it run again, very rapidly you see how the smoke starts being produced, because now it's the polyethylene that is being heated, and quite rapidly, you will see that ignition follows. And once ignition follows, it will continue to burn unrestrained. But as you can see, this is the type of understanding that is fundamental. You start by looking what are the failure modes. You try to understand what those failure modes are. You try to see if there's ways by which you can prevent them. And only then, if you realize that there's some system elements that you cannot describe with these tests, you progress to the next level of the problem. So if you look at the details, basically what is described in this diagram is exactly that. The aluminum composite panel has the two aluminum plates attached to the polyethylene, and while they're attached, they're protecting the polyethylene infill. As soon as the gap gets created and it opens enough to allow for the surface to heat, then immediately what you're going to get is the propensity for ignition. You are effectively going from a condition of LH equals to 0 because the aluminum has eliminated to a condition where LH is the entire surface of the polyethylene. So, as I say, if you look at figure B, this is a different form of the same thing. So this is a ceramic rendered combustible insulation, and you can see how you can achieve fundamentally the same thing. While the ceramic render is intact, the insulation will not burn. That's the image to the left. But as soon as it cracks and opens, then the insulation ignites, and effectively what you get is a complete combustion of the insulation. So there's many ways in which we can achieve this, and all this need to be understood. But if you look at the forms of mechanical behavior and mechanical failure, the figure to the left with aluminum composite panels is the split that is the failure mode. While in the other case is the actual failure of the mechanics of the ceramic rendering. These are two completely different failure modes that are induced by the same heat, but they're behaving in completely different ways. So we need to understand these things before we can look into the performance of these materials. So to me, this is what is fundamental, and I think this is one of those things that in fire safety we have completely forgotten. In any other area of engineering, before we can produce a product, whether it is a mobile phone, a satellite, or a car, we need to demonstrate that the product delivers the functionality it was designed for. So if a car doesn't run, nobody's going to buy it. Or if a phone doesn't connect you, nobody's going to buy the phone. So we have a very clear relationship between product development and functionality. And the same way when we're talking about COVID vaccines, it is a whole demonstration of performance that enables us to actually put the vaccine in the market. And we spend millions in product development. Now, when it comes to fire, we forget that fire safety is a functionality, and that functionality needs to be assessed. And that requires product development, and it requires an investment from the manufacturers in delivering the appropriate functionality for fire. This is completely different than delivering all the other functionalities that you need to deliver, acoustics, thermal, aesthetic, everything, and then see if I can pass the test. It's a completely different process. And I think we need to look at products that are supposed to deliver a fire safety functionality as products that need to be studied, developed, and assessed before they're even introduced into the market. And to me, that is a really, really important thing, because in a way it moves us away from this idea that fire safety performance assessment should always be done the fastest, the cheapest, and the simplest way. Why is this functionality that is so critically important for society so ignored while we're spending millions in making sure that the color of the render is actually the right color? I mean, these are the kinds of things that are difficult to understand, but we really need to be clear that fire safety is a performance that needs to be assessed as a functionality. It's one of the many functionalities that these multi-purpose materials or multi-purpose systems have. So if you think in those terms, then you start thinking there in first understanding the performance of your components, then bringing you to system behavior, and start seeing how the different systems interact. What you see in this diagram is basically a concrete slab with a connection element, with the fixation railings, the glazing. All these components are going to deform and move and interact in a completely different way, and they need to be addressed in a correct and comprehensive manner. Now, obviously, when we address this complex system behavior, we get to a position in which we might require large-scale tests. But nevertheless, a large-scale test is never going to be reality. A large-scale test will always remain a test, and that test is going to provide us with the information that we need to be able to make an assessment. So we can criticize enormously the concept of a desktop study, but what a desktop study is inherently engineering. We take all the information that we have and we make an extrapolation that delivers the required performance. We demonstrate it in a competent way. We explicitly state our assumptions, our dependencies, our conflicts, and we explicitly justify everything we did. Once we've done that, we have done a rigorous extrapolation that gives me confidence that the system that I tested to gain information, analyzed through a desktop study, enables me to confidently establish that I have met the performance criteria. And again, I want to insist that that has to be explicit, and it has to include not only the thermal flammability, combustibility behavior, but also the thermomechanical behavior of the system, because we cannot ignore the deformations. So you can have a perfectly non-combustible material that is an extreme hazard because it deforms and breaks apart very rapidly. Okay? So in essence, I'm not going to go into great detail of this because I know Professor Bisby is going to talk in great detail, but in essence, the tests that were conducted at the University of Edinburgh are an example of how you look into the different failure modes to try to give answers to very specific questions that the chairman had asked from Professor Bisby. So a test was very carefully developed on the basis of an understanding of the system, but also on the basis of a set of preliminary tests that informed Professor Bisby of the different failure modes, of the characteristic behaviors that can be observed. And those set of very small-scale tests with all that information allow him to progress to the definition and the instrumentation of a test of a higher level of complexity. You can call this an intermediate sort of scale test, but it was sufficient to answer the questions that were being asked. The intention of the tests were never to develop a design solution. The intention of the test was to provide answers to very specific questions that had been asked. Now, that particular test provided the necessary informations, that enabled us to be able to, with great certainty, answer those questions in a very precise manner. So, the focus of the tests was in trying to understand the mechanism by which the different components of the system enabled the progression from a system that had an LH equals to 0 to a system that had an LH that was greater than 0 and therefore enabled the uncontrolled vertical fire spread. And what you see from the figure on the bottom left, in the small box, you will see that it's just the full set of data, and you can see how eventually it takes off and it burns at a very large heat release rate. So we are developing a series of tests that enables us to see the failure. So you can see it has failed. Now the question is, what was the process or the sequence that followed, and what were the different elements that influenced that sequence? So you're going to have the basically separation, as I showed, that first manifests itself by a piece of the system falling off, and that's the first little peak that you see in here. You have, before that, you have melting and dripping that produces a flame that is sustaining the process, independent of the presence of an igniter. And then eventually, you're going to get the full failure or the full separation of the panel that happens at this point here, that is going to lead to the takeoff of the fire. Is once the whole system splits that you have the fire taking off. Now, the mechanisms that lead to that are a combination of a number of different things. And as I say, Professor Bisby is going to touch on this in detail, so I will not get into the details. But in essence, what you see in the images to the right is how a system where effectively the fire is not spreading, on the first two images that you have here, is stationary and is only burning because dripping polyethylene is sustaining a little flame, all of a sudden takes off. And the moment it takes off, it becomes uncontrollable. So, understanding failure modes many times is achieved by conducting small-scale experimentation that allows us to understand the failure modes and enables us to design better systems. So if we understand that it is that separation that actually matters, then we can introduce mechanisms to prevent it. And if we still recognize that probably the melting and dripping and burning is still too much of a hazard, even though this thing might not separate, we can actually change the infill for something that doesn't melt. So we can start playing with different things to improve the product until we achieve the functionality. Now, obviously, the small-scale experiments will support larger-scale experimentation because that information then can be used to design and implement a larger-scale test that eventually brings us to understand, the full system behavior. So I am not saying that we have to rely on small-scale tests. I'm saying that small-scale tests are a fundamental and essential part of gaining the necessary understanding so that we can then progress to identify what variables are missing that need a larger scale to be able to assess them. So, for a fire safety strategy that supports a stay-put strategy, we need to now think very carefully what is the target. So obviously there is the condition of no fire spread, but we can also allow a condition of no fire spread until the brigade can enact an egress strategy. So that is a perfectly possible option, but it requires creating that option and creating it explicitly. Now, we recognize that the no fire spread condition is a very difficult condition to attain, and it requires a significant number of constraints that might result in many of the current systems that are very effective for other functionalities having to be simplified, either because the performance cannot be achieved or because we don't have the knowledge base to be able to predict all the different behaviors. So either way, we have to understand that this is a complicated problem, but nevertheless, it is a potential performance target. But if we know that we cannot meet it, then we have to find ways, like for example, what I stated there, to try to be able to establish another mechanism by which we support the fire safety strategy to make sure that we allow for some level of flame spread. In which case, we have to be able to quantify that flame spread. So, as I said, the LH equals to 0 condition is very difficult to characterize. And the other thing that is very difficult to characterize is when you are standing outside a building, knowing when that LH equals to 0 condition has been breached. So that expectation from the fire brigade is one that needs to be looked upon in a very careful way. So if we are going to expect the fire brigades to identify when a departure is necessary, then we need to make sure that we understand when it happens, how it manifests itself, and that we communicate that in an explicit and effective way. So, in the case of a fire safety strategy that supports a controlled evacuation strategy, basically what we're targeting is an allowable rate of spread. And we should be able to quantify the rate of spread. And basically, if we can quantify that, then we can design all the alternative provisions to make sure that our egress times still remain much, much smaller than our available time. Okay? That's the objective. So, now we know what the targets are, and we need to also understand the difference between conformity and compliance. So a building fulfills a fire safety function, and as such, the building has to be compliant. The whole process to the left is a process by which the manufacturers, the people that assemble systems into the building, the construction, all the different stakeholders in the system, from manufacturers to designers to builders, at every stage, we need to be able to demonstrate that and provide the necessary information that shows that the parameters that we're using to quantify our performance are being attained. So if I state that to be able to design a building with a particular egress strategy that requires a particular flame spread velocity, I should be able to provide all the information so that somebody can verify and assess the conformity of that information and make sure that that flame spread velocity is what the material delivers. So in essence, conformity for me is providing in a competent and honest manner, is providing all the information that you need to be able to establish that what you are receiving is exactly what you need. So you have calculations, those calculations depend on certain parameters, depend on certain quantified information, and that information needs to be verified. And if that information is properly verified, then you're confident that your calculation is appropriate. Now, obviously, the verification goes all the way through to the delivery of the project, because obviously it is not the same thing to design something than to actually build it, and implement it, because things can change, things can be modified, or things can not be done at a level of rigor that is not appropriate. And somebody has to be able to establish that it still conforms with the expectations that you have of the performance of that system. So to me, it is extremely important that in the process of understanding the behavior of an external building envelope, it is essential to understand that there's multiple levels of conformity that needs to be met before we get to the building and we establish that the building is compliant. And I touch on this in great detail in my report, because I do believe that there is some element of confusion. And many times we talk about products being compliant. But the reality it is that the building is the one that is compliant, because it's the building that delivers the fire safety strategy. This fire safety strategy is the one that is compliant, and the products are just components that fit there. And there has to be a professional with sufficient competency to amalgamate all that information and deliver a compliant building. And from my perspective, that is the role of the fire safety engineer. Okay? So, in essence, we have the performance objectives, and we have a clear separation between conformity and compliance. And again, that brings us back, to the original question of what is a safe building. But now what I'm going to do is quite rapidly look at this through the perspective of approved document B and our current building regulations, so that finally leaves me with the tests and why they answer the questions or not. So in Approved Document B, we always talk about the 5 functional requirements. And in the case of external fire spread, what we say is that the external walls of the building should adequately resist the spread of a fire over the walls and from one building to another, having regard to the height, use, and position of the building. In other words, the external fire spread or the external walls of a building have to support the fire safety strategy. Okay? And, but Approved Document B has no explicit objectives. Instead, what they do is they have 5 functional requirements. Now, those 5 functional requirements, you can consider them as the pillars of the fire safety strategy. But the reality is that they're just components that need to be stitched by a competent professional that has to be able to marry them in a way such that they actually work together. And this is why when you have a stay-put strategy, it is the stay-put strategy that defines the use and position of the building, and therefore it requires, for B4 to be no spread, unless you put alternative provisions. So all these things are the space in which a competent professional should be able to operate. Now, and as you can see, the space is quite significant, because the reality is that B1 to B5 are only the tip of a very, very large iceberg, of assumptions, dependencies, and conflicts. So we need to be able to engage with these things in an appropriate way. Now, the compliance is compliance with the fire safety strategy. So it is the fire safety strategy that is compliant with a set of objectives that unfortunately remain undefined. And what is a safe building is the question that still remains undefined. Nevertheless, we have to show compliance against that performance criteria. So in many ways, you're almost saying that you have to assess compliance to the comfort of the competent professional, which is a very tricky proposition because it puts an enormous onus on competency and therefore an enormous need for properly regulating competency. So then the fire safety strategy sits on all these pillars, and these pillars then have behind them a series of potential approaches. Okay? And we're all very familiar with those potential approaches. You've seen those diagrams again and again and again, but they're just potential approaches. Nevertheless, despite the fact that they're potential approaches that are based on major assumptions, that have major limitations, that hide complexities, that hide dependencies, that hide conflicts, we have to extrapolate those guidance into something that enables us to define a comparative level of safety. And interpretations, as you can imagine, can be very broad and therefore very, very problematic. So in essence, without an overall objective for the fire safety strategy, there's very few mechanisms other than professional competency that enable us to be able to establish what is a safe building. So if we cannot establish what a safe building is, then how can we link this to the physics of the problem? Here we have a very complex physics with a lot of different variables, and we have to be able to establish that this building envelope provides me a mechanism to support the fire safety strategy so that it delivers a set of unknown objectives. So for a test to be useful, we have to clearly establish the phenomena that needs to be quantified and the tolerable error and uncertainty. We can do that. So the physics is there. It might be very complicated, and we might not be able to do it for the most complex systems, but we could actually do it for a number of different systems, and we can actually do it right. We can establish errors, and we can establish that we have confidence that we've put enough safety factors to be able to be in a safe place. So that we can do. we have to understand the relationships that govern the phenomena. We do that. We understand the relationships. We know what is a flow in a cavity, and we can understand what a flow in a cavity is. We know how to stop it. We have tools to do these things, and we can even set targets like LH equals to 0. Now, the next step is that we have to extract from these relationships that the parameters that influence the phenomena. And here's a list. You have in this box all the parameters that influence the phenomena. You have to determine the measurements necessary to define and infer the parameters. Professor Bisby did that with the tests that he conducted. So you actually can do it. And you have to demonstrate that all inferences are unique, and you understand all your errors and uncertainties. We know how to do this. So the physics is there, it has been studied, it has been recognized, and we know how to do it. Which is a very different proposition, is are we competent enough to apply this information? Nevertheless, the problem is that if we don't have a clear target, even then we can be as competent as we want, and we really don't know exactly how to use this information. Now, instead, we resort to surrogates. And I talked about maximum egress distances, I talked about velocities. These are all surrogates. Tests are surrogates. Performance in a test becomes a surrogate, and if we don't understand all the assumptions behind them, it is very difficult to relate the surrogate to the real performance variable that we're interested in. Now, our tests, currently the existing tests, can be input tests, which are basically a test that I conduct to extract a parameter. Maybe 2, 3, multiple parameters, but I want the test purely to extract information that then I can input into a model. And it is the model that gives me the performance. That's what we call first principles design. So I can construct a mathematical formulation that describes what is the flame spread velocity. But that mathematical formulation requires the T ignition, it requires the thermal inertia, it requires the parameter phi. And I'm going to use tests to assess what is the value of phi, what is the value of the thermal inertia, and what is the value of the ignition temperature. Then I input them in the model, and I can calculate the flame spread. Okay? So that's an input test. A bounding test is the fire resistance test, where you find what is the worst possible scenario, the hottest fire for the longest duration. And if my system survives that, I can have certainty and confidence that it will survive any other fire. That's a bounding test. So I've created a worst-case condition that allows me to bound the problem. And then there's the scenario tests. The scenario tests are the most complex set of tests because you need to be able to first establish that the scenario is representative of the condition that you want to study. Then you need to be able to establish that that test is going to provide you information that is valuable for you to be able to extrapolate performance. And then finally, you need to be able to make sure that you are making the measurements and the analysis that is appropriate for that extrapolation. So scenario tests are focused on the idea of reproducing reality, or some form of reality that can be extrapolated to reality, to the real reality. Now, a typical example of an input test is the one followed by the linear route, or the difference between non-combustible and combustible. So if I conduct a test, and that test determines that the heat of combustion is so small that it can be neglected, and therefore the material will not burn, then the rest of the problem, as you can see from this diagram, disappears. Okay? That particular problem now is limited to the fact of establishing this, and the problem that I have solved is the problem of combustibility. So in other words, it is not going to burn. That doesn't mean that the system is going to perform correctly. All that means is that that material has a heat of combustion that can be neglected. Okay? So that's an input. So if I have a model, the model becomes in many ways useless because the key parameter is 0, and you multiply anything by 0 and it's going to give you 0. So in principle, I don't need a model. The model is very simple. If I want to assess combustibility, I have a simple test that is an input test that gives me the heat of combustion. So it's a perfect example of how you can take some information and extract something that is of value. Now, this is where the confusion comes in, because then you use terminology like limited combustibility. Limited combustibility requires to create a threshold, okay? But the moment that the heat of combustion is not zero, you cannot cross anything. What happens is that the problem now exists, and unless you analyze the entire problem and come into a position where you either establish that the flame spread velocity is adequate or LH is equal to zero, you cannot claim that because it's limited combustibility, it will deliver the performance that you need. You still have to do the full analysis, because at the end, your performance is defined by LH equals to zero and the flame spread velocity. So if you don't do all the analysis, limited combustibility by itself has no meaning. Now, if somebody has done the analysis and established a clear threshold, and that clear threshold has been demonstrated, then you can simplify the problem and then classify it as limited combustibility and deliver a simpler version of an analysis of something that we already understand. Now, in the absence of that analysis, that cannot be done. And in essence, that analysis, unfortunately, when you have complex systems, becomes part of the design process. So this is a perfect example of an input test that can deliver you something that can be tweaked in a manner that gives something that is potentially, in the absence of an analysis, not satisfactory. So class zero is a very similar example, because it is really not an appropriate approach to characterize what the test aims to characterize. So this is a test that aims to characterize surface fire spread or surface flame spread. Nevertheless, the whole configuration of the test does not reproduce the system behavior, does not reproduce the failure modes, does not have any of the characteristics that enables me to understand when LH stops being zero. If what I'm testing is an aluminum plate, that aluminum plate will always give me LH equals to zero. But if I put polyethylene behind an aluminum plate, then what I'm interested is when it splits. That's the failure mode that matters. Not the result of a test that effectively is testing the aluminum and is not testing the system behavior. So again, the combination of the two standards set an arbitrary threshold for the heat of combustion that has no relationship with what follows after. Because once I have heat of combustion, I have to calculate everything. And the flame spread test does bear no reflection of the failure mode that I need to understand. So in principle, that test provides me no information. It's meant to provide me information, and I could instrument a test that is very similar. I could change the way in which I arrange the frame. I could do a lot of different things to improve that test and obtain valuable information. But used in a standardized way, effectively for this type of products, doesn't give me the information that I need at all. So it doesn't give me any information on how to establish LH, and it gives me no information on how to establish a flame spread velocity. Now, finally is BS 8414 and BR 135. This is a scenario test, and we can criticize the scenario all we want. We can criticize the way in which the system is assembled all we want. Nevertheless, it's a test that attempts to reproduce a scenario. And as BR 135 establishes, it leaves it to the interpretation of the competent professional. So BR 135 does not establish a passing criteria. BR 135 establishes failure criteria, beyond which there's no hope. So if that happens, then you don't want to use this material, and we have the right, to cut the tail. Okay, that's a right that we have. But beyond that, the test is just the test. Now, there is no assessment that comes with the test. That is up to the competent professional. So the competent professional has to determine what the objectives of the test are, because without really having a clear objective, it's just a test for the sake of running a test. So what is the information that they want to have? If they want to understand how cavity barriers work, then they need to set the test in a way such that they gather information of how the cavity barriers work. If they want to understand how the insulation contributes to the burning, of the external cladding, then they have to provide the appropriate information to be able to understand that. Maybe it's an analysis of the system, but there has to be an explicit analysis, and there has to be explicit data and information and instrumentation. So before conducting a BS 8414, it has to be very, very clear what the objectives of the test are, and how to embed that concept in what is the risk that is represented by flame spread. It could be surface, it could be cavities. All the statements are there in BR 135. Nevertheless, the statement that is missing is the role of the competent professional in determining all these details. The test, as it is purely just a test. Now, as I said, the test doesn't have passing criteria, it just has failure conditions. And that's perfectly fine. You can create failure conditions as a mechanism to eliminate a certain tail that you deem from the onset, no matter what the objectives are, as unacceptable. But the fact that you don't fail according to the failure criteria doesn't mean that you have met the performance criteria associated to your particular fire safety strategy for your particular design. That is left to the competent professional to establish. So we have this failure criteria, and I have no objections, to the failure criteria, other than the fact that mechanical performance is treated in such a summary way that in principle leaves a lot of space for potential failure modes that are not captured at all in a test that is deemed to be a system test. So if it's a system test, then you need to incorporate all the potential failure modes. And this is where the whole sequence comes in. If I have done a proper product development, trying to understand the functionality and how it works, and I have progressed that from the small scale through an intermediate scale until I have confidence that my system is going to operate, I'm going to know exactly what I want to get out from the large-scale test. If I have not done any of this background work, there is absolutely no way that a large-scale test that is very ill-defined, because you don't know exactly what you're looking for and you don't know exactly what you're measuring, is going to provide you the information that you need. So at the end, it is about incompleteness of the information. A facade system might not reach the BR 135 failure criteria and yet still be entirely incompatible with the fire safety strategy of a residential building with a stay-put policy in place. And that, I think, is something that I would like to make absolutely clear, that the fact that it doesn't reach the failure criteria doesn't mean that the system in its application meets the performance criteria. The information provided by the thermocouple arrays is very, very limited. And I don't need to go through the details. All this is in my report. But at the end, this test that we need to have that enables me to establish that the flame is not going to spread and is going to support the stay-put strategy, or is going to spread at a certain rate that is going to support an evacuation strategy, is not information that is collected in the test. You can argue that by looking at 2 data points, you can establish some sort of flame spread velocity. But the reality is that if you are to do that, then you are accepting that if I put 10 more thermocouples and I actually measure the proper flame spread rate, and I can fit it to an appropriate model that can allow me to predict what happens after you exceed the height of the test, wouldn't that be much better? So in essence, we have a test in its minimum expression with this minimum amount of data, and we are arguing that we can extract information that is so much more refined because it depends on so many variables that requires a much more extensive set of measurements. Then why not just do them? Why do we need to stick to the minimum expression when the risk is so significant? So to me, this is a really important aspect. And in both the case of the stay put strategy and the case of the evacuation strategy, the information that you extract from BR135 is very, very limited. At the end, there's another aspect that needs to be addressed, and you will find out, and I put a citation in there, that is great controversy on whether this scenario is an appropriate scenario or not. Here we have 3 examples of very similar tests. The left-hand side is BS8414. Sorry, the number is wrong. There's NFPA 285 and the FM Global test. And you will see in the figure on the left that each test has a very different description of what is the heat flux that you need to apply. So whether we are applying an appropriate scenario is still a matter for debate. And I'm not even arguing that this scenario as it is cannot be used, but already in itself, understanding to what extent it describes the appropriateness of the scenario is something that needs to be done. Because, we have the data, we know what this decay is, and we know what the peak values are. So why we cannot characterize and say, well, this test applies for this type of conditions that leads to a value that is more or less this value in this position. But that information is still unavailable. So in essence, the test provides very limited information. The final test that I'm going to look into is the European Reaction to Fire Classification Test. And this is a test that was developed for a very specific purpose, which is to try to understand the propensity for flashover. So that was the objective, that was the scenario. And the test that was used to define that scenario was the room corner test, which was a large-scale test. And a very large amount of data was produced to establish a very good correlation between a classification, which is a simplification of a well-understood problem, that enabled them to establish a classification for propensity to flashover. Now, the test, through a benchmarking study, was shrunk to a level where it produced better data, it was more consistent, and it was at a scale that was more practical. And it was demonstrated through this benchmarking that actually the classification matched. And you could actually get use the same classification for the SBI and be able to predict the propensity to flash over. Okay? The phenomenon of flashover is very different to the phenomenon of vertical flame spread. It's controlled by very, very different parameters. Now, therefore, that classification that is meant to be for the purposes of addressing flashover cannot be used to try to address vertical flame spread. So it's just simply the use of that classification is what is inappropriate. Now, the test has a lot of good measurements, has a lot of good data, and potentially there's information that can be extracted from the test. And it could be perfectly appropriate for people to use that information in such a way that they can conduct an appropriate analysis to establish the performance criteria that they need. But it is not to be used as a means to classify, extrapolating a classification that was intended for a completely different scenario. The variables are different, and the classification therefore provides no meaningful information. As I said several times, none of the current performance assessment testing procedures addresses the formations, thermomechanical behavior, or failure of the encapsulation. And given the strong dependency of mechanical performance and encapsulation, the absence of this performance criteria represents a serious limitation to everything that we're doing today. So whether we understand combustibility and whether we understand how to design combustible systems, in many ways is very limited by the fact that we still don't even understand how to design non-combustible systems. And unless we put focus on how to design non-combustible systems, we are constantly introducing failure modes without paying any attention whatsoever. So the real question is, how did we get there? And this is a diagram that is in my report, and the only information that this diagram shows you is how through the years knowledge has lagged need. You know, we've been building buildings way before Faraday understood a candle, and we've been creating tests way before we understood ignition, combustion, or flame spread. Beyond that, you know, way before we even we needed all this information before we even professionalize the discipline of fire safety engineering. So IFE doesn't come in until 1918, the American version SFPE until 1950. And there's a long, long history of us doing always the same thing. If you don't understand anything, burn the entire building. That's the process that we've been following. That's the advice that we have been following, you know, for decades and decades and decades. If you don't understand, burn it. You know, that is the way we've been operating. Now, the one thing that we need to recognize is that if we look at the end of the timeline, we've caught up. So now we have most of the knowledge, but what we haven't changed is the mindset. And we're still trusting those who tell us, if you don't understand, burn it. And that's not the case. You know, we can understand, we can set the performance, we can set the functionalities, and we can actually come up with a proper calculation, a proper desktop study that actually uses all the information that is available to actually deliver a conformity to the performance that we expect. So this is how we got there. And I think we need to change that mindset, because until we change that mindset, fire safety is never going to be seen as a functionality. It's going to be seen always as just the last stage of the whole process, the one that we want to do very rapidly, where the only good answer is don't change anything, you know, where effectively it's all about cheap, fast, and simple. And we have a very complicated problem that cannot be addressed in those terms. So, explicit performance objective, again, I go back, you know, we need to know what a fire-safe building is. You know, how fire safety performance is expressed in building regulations, now we understand it. You know, it is expressed in a way such that leaves an enormous space for the professional to exercise their competency. Nevertheless, we have no idea who is the person that we expect to deliver this knowledge. And if we look at what we do, you can see in the column on the left, on all the yellow things, the performance objective remains a matter to be defined by competent professionals. The overall safety objective and fire safety strategy have to be defined by the competent professionals by blending these pillars in a way such that it is coherent. You know, the requirements, how requirements B1 to B4 support the fire safety strategy, therefore, is defined by the competent professional. Interpretation of guidance and supporting testing, you know, to be able to extrapolate or in one way or another one compare performance, again, is determined by the competent professional, and the applicability and validity of guidance and supporting testing to be defined by the competent professional. In other words, the onus on the competent professional is enormous. At every level, all the gaps need to be filled, and all those gaps require a very, very high level of competency. And as I said, in an area that is multidisciplinary and that it requires a very significant understanding of multiple different problems that go from human behavior all the way to legislation. So we have to be quite careful. So in summary, I would just like to end by saying that knowledge in support of fire-safe buildings is currently available, and the traditional practice of regulating before understanding is no longer necessary. So documents like PAS 9980 unfortunately still follow that approach, and I think we need to be very, very careful in the way in which we use them. Performance testing for systems delivering fire safety functions should be done as part of product development and then assessed for conformity. It's not about compliance, it's about making sure that whoever is developing a product is providing you with all the information that you need, and that information is verified. And materials, products, subsystems, and systems have to be assessed for conformity, and it's the fire safety strategy that has to be compliant, because that's the functionality that we want at the end. That is the performance requirement. So current building regulations put an extraordinary weight on competent professional practices. This is inconsistent with the weak professional competency framework that we have currently in use. And this is where I end by telling you, I'm a mechanical engineer. I have 3 degrees in mechanical engineering. I can stand in front of you and argue endlessly how competent I am, but the reality is that it's going to be up to you if you believe me. And the problem is that other people will stand in exactly the same place, coming from different backgrounds and arguing exactly the same things. And if you don't understand what competency is, and we don't have a clear definition of competency, we create a confusion of competency that ends up devaluing the capacity of people, because a competent individual recognizes complexity, recognizes the implications of their decisions, and therefore proposes solutions that are complex in nature, that require deep analysis and deep thought. An incompetent individual is unaware of his incompetency. They provide simplistic solutions that are cheap and fast. And the problem is that if we don't define competency appropriately, at the end, people like me or other people are going to be standing in there and we will not be able to tell the difference. So I hope that I have clarified my report, and I'll be more than happy to answer all the questions when the time comes.
Professor, thank you very much. It's been a very interesting morning. Thank you.
Thank you.
Ms. Grange, do you want to say anything else at this stage?
No, we can break for lunch now, and then we have a presentation from Professor Bisby this afternoon.
Right. Well, thank you much again,
Thank you very much.
Professor Torero, and we'll see you again next week when you are asked to answer some questions in relation to your report.
Thank you.
Thank you very much. Yes, thank you very much. Well, we'll break at that point and we'll resume at 2 o'clock, please.
Yes, thank you.
Thank you very much.